The current state of software assurance is dire and stems from a combination of neglect and unmet need. The future state of software assurance needs to feature smart and trusted methods and metrics, including software assurance risk calculation that is precise, accurate, timely, and complete. Some unmet need is due to lack of adoption and some lack of technology. Lack of adoption falls on both industry practitioners and government acquisition specialists. Neglect is on glaring display in the intentional practice of technical debt, spurred on by a misguided culture of acceptance. Furthermore, the shortfall of STEM workforce yields a persistent level of unintentional neglect based on ignorance. Beyond software assurance adoption, the focus areas most in need of attention are build security in, resiliency, advanced technology, and renovation of the CMMI to address software assurance. Software assurance means the level of confidence that software functions as intended, and only as intended, and is free of vulnerabilities, either intentionally or unintentionally designed or inserted as part of the software, throughout the lifecycle. Concrete software assurance objectives with consequential outcomes include components that are provably correct, demonstrably free of weaknesses and cybersecurity vulnerabilities, and demonstrably free of improper proprietary information, copyrighted material, and trade secrets. The current state of software assurance is dire and stems from a combination of neglect and unmet need. The future state of software assurance needs to feature smart and trusted methods and metrics, including software assurance risk calculation that is precise, accurate, timely, and complete. Some unmet need is due to lack of adoption and some to lack of technology. Lack of adoption falls on both industry practitioners and government acquisition specialists. Neglect is on glaring display in the international practice of technical debt, spurred on by a misguided culture of acceptance. Furthermore, the shortfall in STEM workforce yields a persistent level of unintentional neglect based on ignorance. Beyond software assurance adoption, the focus areas most in need of attention are build security in, resiliency, advanced technology, and renovation of the CMMI to address software assurance. The kernel of the layered defense approach to software assurance is structured programming and the rigorous and provably correct use of 0 and 1 predicate prime programs, along with proper programs composed of multiple prime programs limited to single entry and single exit. The layered defense approach recommended here includes defense in depth, build security in, risk management calculation, and resilience. Defense in depth is composed of encryption, identity management, access control, authorization management, accountability management, incident management, configuration management, and security assurance operations. Build security in is composed of structured programming with emphasis on correctness, cleanroom software engineering, and statistical testing, static analysis tool use, function extraction tool use, common weakness and known vulnerability evaluation. Risk management calculation includes goal identification and actually calculating risks based on systematically distinguishing factors, sources of risk, and problems using levels of confidence. Resiliency prerequisites are defense in depth, business continuity, and survivability, and features of resiliency include coordinated recovery time objectives, digital situation awareness, distributed supervisory control, selective availability, operation sensing and monitoring, information and data recovery, and interoperability of data and information exchange. The practice of technical debt fosters permissible and persistent neglect and needs to be discontinued and eliminated. Technical debt is the organizational, project, or engineering neglect of known good practice that can result in persistent public, user, customer, staff, reputation, or financial cost. While the CMMI provides an excellent platform for achieving widespread adoption of software process maturity, it is incomplete with respect to software assurance and cyber security process. The importance of underutilized technology lies in the potential of the CMMI and its widespread infrastructure of usage to serve as the platform for software assurance adoption and dissemination. With respect to defense in depth, encryption, authorization management, and security assurance operations are underutilized practices. In addition, three-factor authentication based on what you are, what you have, and what you know is an underutilized technology. Finally, trusted encryption advances are needed. The table also highlights the advanced technology needed, and here, defense in depth awaits trusted encryption advances. With respect to build security in, there are numerous underutilized practices, including structured programming, with insufficient emphasis on correctness and proof of correctness, and inspections, with well-defined standard of excellence spanning completeness, correctness, style, rules of construction, and multiple views. Cleanroom software engineering and its underutilized practice, and statistical testing and its underutilized technology. Function extraction and its underutilized practice and technology, and its need for advanced technology. And underutilized practice of common weaknesses and known vulnerabilities, and the need for additional advanced technology. With respect to structured programming specifically, the rigorous and provably correct use of 0 and 1 predicate prime programs, along with proper programs composed of multiple prime programs limited to single entry and single exit, is the kernel of trustworthy software assurance. The table highlights the advanced technology needed. Static analysis needs commonality and interoperable tool vendor results post-processing advances to disambiguate multi-vendor results and decimate the number of false positives. Function extraction needs to be able to process large programs and systems, such as those found in legacy software systems, COTS, reuse libraries, and commercial software releases. In addition, function extraction needs to be able to process source code from a wide range of languages and object code from various instruction set architectures. Common weaknesses and known vulnerabilities need to be integrated with static analysis tool automation. In the legal community, the abstraction, filtration, comparison test is a three-step process for determining substantial similarity of the non-literal elements of a computer program. The illegitimate use of proprietary information, copyrighted material, and trade secrets needs to be detected by NIST's approximate matching using text strings to detect fragments, and ORNL's Hyperion using behavior specification units for detecting intended functions. With respect to risk management calculation, while goal identification is commonplace, actually calculating risks based on systematically distinguishing factors, sources of risk, and problems using levels of confidence is an underutilized practice. Beyond that, determining the level of confidence in assigning a failed state to a factor is assisted by evidence-based assurance assessment questions. The table highlights the advanced technology needed, and here risk management calculation needs to apply cognitive systems, that is, IBM Watson, with its emphasis on levels of confidence useful in calculating risk. With respect to resilience, coordinated recovery time objectives digital situation awareness, selective availability, and data and information exchange represent underutilized practices and features. The table highlights the advanced technology needed, and here, resilience needs to apply cognitive systems, that is, IBM Watson, with its potential for anticipation, avoidance, and digital situation awareness. A Center for National Software Assurance, CNSA, would attempt to understand the past and current directions of the software profession in order to anticipate next-generation software engineering and to guide its impact towards consequential outcomes in security and competitiveness of the nation's critical industries. Currently, the state of software and software assurance are dire. The line of sight for a target organization adopting software assurance is guided by a 5-level maturity value map, including defense in depth, build security in, risk management, calculation, and resilience. Level 2. Defense in depth, including standards for existing methods and practice for assuring software security focus on protection from vulnerabilities and threats through security in depth. Protective measures include encryption, identity management, access control, authorization management, accountability management, incident management, configuration management, and security assurance operations. Level 3. Build security in, including standards for existing methods and practice for trustworthiness, focus on building security in by constructing software components, systems, and systems of systems to an engineered standard of excellence based on completeness, correctness, and rules of construction. Beginning with discontinuing the practice of technical debt, build security in practices include structured programming with an emphasis on correctness, cleanroom software engineering and statistical testing, software inspections process with well-defined standard of excellence, the application of static analysis tools, the use of common weaknesses and known vulnerabilities, and the application of function extraction. Level 4. Risk management calculation, including standards for existing methods and practice for calculating software assurance uncertainty, focus on factors, sources of risk, and problems evaluated for each goal. Account of factors that might serve as sources of problems in goal achievement, and account of factors that represent objectives that are in a failed state. Determining the level of confidence in assigning a failed state is assisted by evidence-based assurance assessment questions. For each goal, the calculated risk is the number of problems divided by factors evaluated, expressed as a percent. Level 5. Resilience of systems and supply chains, including standards for existing methods and practice for assuring resiliency under stress. Focus on anticipating, avoiding, withstanding, mitigating, and recovering from the effects of adversity, whether natural or man-made, under all circumstances of use. Features of resiliency engineering include coordinated recovery time objectives, digital situation awareness, distributed supervisory control, selective availability, operation sensing and monitoring, information and data recovery, and interoperability of data and information exchange. Trustworthiness requires a commitment to rigor in both software production and its verification. No soft skill. Rigor has a hard edge. In an environment of neglect and unmet need, the introduction of rigor would be a game changer, one that requires both cultural change and engineering know-how with pass-fail training certification. Software assurance demands two capabilities associated with trustworthiness: the capability to produce trustworthy software products and the capability to verify that software products are trustworthy. Each depends on engineering technology rigorously applied. The table evaluates the build security and methods discussed in terms of degree of rigor, suggesting a ranking of rigor as first tool automation, then engineering, and finally process. Not just tools in a toolbox, the build security and methods represent the core competencies that serve as the center point for trustworthiness and rigor. A straightforward assessment of enterprise commitment to these software assurance core competencies can be found in the following questions. Number one, to what extent has the organization adopted structured programming and explicitly applied it in practice? Number two, to what extent has the organization adopted correctness by construction and expertly applied it in practice? Number three, to what extent has the organization adopted clean room software engineering and expertly applied it in practice? To what extent has the organization adopted the evaluation of common weaknesses and known vulnerabilities and expertly applied it in practice? Number five, to what extent has the organization adopted a defined standard of excellence and expertly applied it in practice? Number six, to what extent has the organization adopted static analysis and expertly applied it in practice? Number seven, to what extent has the organization applied statistical testing and expertly applied it in practice? Number eight, to what extent has the organization adopted function extraction and expertly applied it in practice? The layered defense approach recommended here includes the defense in depth, build security in, risk management calculation, and resilience engineering and processes dependent on an elevated state of software engineering rigor. There is much room for improvement in the rigor of software assurance methods and practices capable of delivering consequential outcomes, including components that are provably correct, demonstrably free of weaknesses and cybersecurity vulnerabilities, and demonstrably free of improper proprietary information, copyrighted material, and trade secrets. Software assurance is impeded by the acceptance of technical debt, a practice that breeds neglect and should be discontinued. Advancing software assurance adoption would be stimulated by renovating the CMMI to include software assurance and cybersecurity process capabilities. Strengthening defense in-depth encryption, authorization management, and security assurance operations practices are needed. Build security in emphasis on correctness proofs and the defined standard of excellence for completeness, correctness, style, rules of construction in multiple views is the required foundation for the increased rigor being sought. The full utilization of statistical testing, function extraction, and static analysis automation would verify and calibrate the improvement in rigor and cost effectiveness in schedule efficient manner, enabling the next generation software engineering goal of doing more with less fast. Much needs to be done on resilience, including the widespread implementation of resiliency functions and features. The CNSA would be organized to drive the software assurance initiative and would be established to elevate software assurance to the national agenda across industry, government, and academia, and addressing issues of national importance in security and competitiveness. With genuine attention and care taken in team building in forming a software assurance steering group, its initial focus would include the establishment of its program of operation, the recruitment and sourcing of staff, and the identification of issues of national importance, and the formation of working groups needed to address critical software assurance issues. A governance model would ensure the DoD focus needed to deliver consequential outcomes in the technical capabilities that promise to reduce the cost, acquisition time, and risk of major defense acquisition programs. Here is my contact information. I would be happy to receive questions and have discussions with people on this important subject.